я хотел поговорить вот о чем. Вот на поверхностях. На поверхностях. Обычной поверхности. Многообразие размерности. Многообразие размерности 2.
Владимир Георгиевич, наверное, на английский стоит перейти.
Извиняюсь. So, surfaces. I wanted to talk about surfaces, which are just manifolds of dimension 2. Surfaces are oriented. I will always understand that they're oriented. And on surfaces, there are many interesting algebraic structures. First structure, if you have one surface, say sigma is a surface. The first structure is homological intersection. Homological intersection. If you have two loops on the surface, say directed loops A and B, then you can compute the homological intersection number A times B, which is an integer. And this gives you a skew-symmetric bilinear form. What happened? Oh. This gives you a skew. You still don't see me now?
We don't see. The video disappeared
Something happens
6
here.
seconds ago. Oh, we see it again.
All right. So that's skew-symmetric bilinear form. Skew-symmetric bilinear form. Which is, of course, a very special case of homological intersection in all dimensions, in all manifolds. Now, a more interesting and specific to dimension 2 is so-called Goldman's bracket. So it appears only in surfaces. So first of all, you consider the set of all free homotopic classes. So it's no more homological invariant. You consider, let it be P is a fundamental group of sigma. P hat is a set of conjugacy classes of elements of this group. Conjugacy classes. And then you take the module M is the free module with basis pi hat. Now, what the bracket here is a bracket in this module M. Well, a module, it's just an abelian group. So M cross M to M. Now, how it happens? On generators, if we have two loops, example, one loop, let it be alpha, and another loop, let it be beta. So these are two loops in the surface. We consider all intersection points. So let's take one intersection point. Here we have the tangent base, the tangent vector of alpha and the tangent vector of beta. So this pair of vectors determines the sign, plus or minus. Now, when it is plus when the direction from alpha to beta coincides with the direction of sigma. And when it is minus, in the opposite case, when the direction of alpha followed by the direction of beta at this point is negative. So we get a sign at this point, let it be P. But also we have a loop. Namely, we start at this point and first go along alpha until coming back, and then go along beta until coming back. It gives you a loop based at P. And that is for all intersection points. Now, the bracket is defined as the sum of those loops. So the sum of all crossing points, the sign, so that's plus or minus 1, determined by orientation, times this loop, which I just described. So you take alpha, based it in P, so follow along alpha starting and ending in P, then multiplied by the loop beta starting and ending in P, and then we take the free homotopy class or the conjugacy class of that loop. Beta P. So that's so to say product of these loops based on this point P times the sign and sum up of all P's. Now it turns out that this thing is well defined. So it does give well defined pairing like that, and moreover that's a theorem due to Goldman. This bilinear form is a V bracket. That's the most extraordinary construction. Now, where it comes from, you may think of loops as functions. Every loop determines just a function on the Teichmüller space or on the space of representations of the fundamental group. And that is, this Lie bracket reflects the Poisson bracket on that Teichmüller space. So it comes from there. But the construction is purely elementary. You don't need to know representation spaces or anything else. Okay. But there is another structure which is my own co-bracket. Let me call it T co-bracket. So not only there is a Goldman's bracket, but there is also a co-bracket. So the co-bracket is something like this. You start from M and go to M tensor M. I'm going to denote it by nu. Now, how this is defined? Now you start with only one loop. you take one loop, say alpha, and you consider all self-crossings. Now, when you have, let it be S. S is a self-crossing. At each self-crossing, the loop is split into two subloops. Alpha 1, or well, let's say, it depends on S. It starts and ends in S. You go along, let's say, half loop. One of them is alpha 1. The other one is alpha 2. So the alpha 2 is the other one. Alpha S2. You start from S, go along alpha until coming back to S, but then you stop. So that's alpha 2. Which one is 1 and which one is 2 is again determined by the orientation of the surface. The pair of tangent vectors should be a positive pair with respect to the orientation of the surface. And now nu of alpha, the co-bracket, is the sum over all crossings of alpha of the tensor product alpha 1 S tensor alpha 2 S minus alpha 2 S tensor alpha 1 S. The sum over all self-crossings. Now it is well defined, and it is a Lie co-bracket. Now I'm not going to recall what is the Lie co-bracket, just enough to say that that's a notion dual to the notion of Lie bracket. For example, you see it is Q-symmetric, and it satisfies also the dual version of the Jacobic formula. Moreover, so that was my theorem proved, I don't know, so 30 years ago, the Goldman's Lie bracket and this Lie co-bracket, together, they are compatible in some sense. And this sense is usually formulated by saying that this is a Lie bialgebra. A Lie bialgebra. Well, all these notions which I don't define, you can find easily in the literature. So, which means that this is a Lie algebra, this is a Lie co-algebra, and they are compatible in some way. All right, that was known for a long time. Now I got interested in so-called quasi-surfaces. What is a quasi-surface? Quasi-surfaces. Again, you take a surface. So, for example, that's a surface. Now that's a boundary. And on the boundary, you take several segments and glue these segments to an arbitrary topological space. So basically, the idea is that the piece of our space is a surface, and the complementary the complement of it is a kind of black matter. So some topological space which is not surface at all. So there is a good part. A good part is a surface. There is a bad part. A bad part is something, we don't know what. And the question is, can we do still anything, as I explained before. Can we do for quasi-surfaces something similar? Well, the answer is yes, we can do it. It is done in my preprints, for example, the last one was published in 2020. Loops, you can see from the title, quasi-surfaces are things, strange things like that. Quasi-Lie bialgebras are analogs of those structures for them. Now, first of all, homological intersection. Suppose we have two homological classes. What we do with them? So we have two loops, just like here, like we did on surfaces. Can we do something on quasi-surfaces? Well, the answer is yes. You do it in several steps. First of all, you have two loops. Let's say AB loops in this quasi-surface. Let it be Q or quasi. So they sit inside the surface part, but may go from time to time, they may go to this bad part about which we know nothing and cannot do anything. Now, to go from the surface to this bad part, we need to cross these segments. So these segments, therefore, I call them gates. So gates. So there are two gates here on this picture. Now the gates are segments, they can be oriented. Let's just fix an orientation of the segments. So omega orientation of the segments. And of course, the surface sigma itself should be oriented, otherwise we cannot do anything. Now the idea is this: you can push the loop A so that it crosses every gate near the beginning of the gate, and we push the loop B so that it crosses every gate near the end. So basically near every gate, A goes like that at the beginning, and B goes like that near the endpoint. All right. After that, we can define the new crossing. So basically what happens is that when A crosses a gate and B crosses a gate, each such pair of points can be considered as a kind of intersection points, kind of intersection of A and B. Kind of intersection of A and B with respect to this gate. With respect to this gate. Now, so what we do? I'm looking for the way how I wrote this. So what we do, A dot B, first of all, by definition, is the sum of everything which happens inside the surface, A dot B. Well, the sign epsilon R of AB inside the surface. So R are points like this. And we take every point at a gate, every point where A crosses a gate, B crosses a gate, that's a point Q. So that's a point P, that's a point Q, and sum up over all these people. So here PQ intersection with this, it's the same gate. And yes, each loop crosses the gate either from sigma, from the good part to X, or it goes from the bad part to sigma. So there is a sign which indicates the direction of the loop, and this point P, it is plus if the loop goes from sigma to X, and it is minus if the loop is directed from X to A. And we take the product of these people. And there is one more sign, which depends on omega, on the orientation, epsilon omega, which is the compatibility, whether the orientation of sigma, which is orientation here, is compatible with the orientation of the gate or not. So it's there are three signs. We multiply them. So let it be the gate number K. Gate K. So this depends on K. PQ are intersection of these loops with K. And then we sum up over all Ks. Well, it turns out that that's well defined. What it gives us, well, a kind of intersection, H1 Q. Q is the whole thing, times H1 Q to Z. So Q is the whole space, but still there is some kind of homological intersection which is determined by the nice part of this Q, right? So let me denote this somehow by, so that's a dot, but this dot depends on omega, on the orientation of the gates which we fixed. So that's dot omega. Now, the interesting part is that this is not skew symmetric in general, but you can skew symmetrize it. So a new dot is this omega dot minus y, this omega dot x. And this is for all x, y in H1. Now, the claim is that this dot without omega actually does not depend on omega. So the gate orientation is needed to define this omega dot. When we skew symmetrize it, we get something independent on the gate orientation, which means, well, we have something which is in some pairing, which is inherently associated with that space. Now, in the case when there is no bad path, so we just have the surface only, we get twice the usual homological intersection. So this thing generalizes the usual homological intersection for quasi-surfaces. Now we can ask, can we do similarly? Can we act similarly with the Goldman's bracket, with the co-bracket, and with the pair? If yes, what would it mean? It would mean that we can get a notion of Lie. Instead of Lie algebra, we get something different, more general, what I call Lie quasi-bracket. We get Lie quasi-co-bracket, and here we should get Lie quasi-bialgebra. So the idea is still the same. We have those gates, we orient them. One loop always goes on the left, towards the beginning of the gate. The second loop, yeah, I'm just talking about the Goldman bracket. How to define the Goldman bracket in this case? Of course, we have this part. That is the part which happens inside the surface. So inside the surface, it's still the same thing. So we have this quasi-surface, well, some handles, gates. Well, there may be any number of gates. Well, the bad part, some space X where all this is glued. And then we want to define an analog. We have two loops, alpha and beta, two loops. And then we define the bracket alpha beta. Well, the idea is the same as before. The same as before, but well, with minor corrections. So let me see. We have intersections of these loops, and each intersection gives a term, contributes a term. We have those gates oriented. Again, alpha, the first loop, goes near the beginning. We push it, deform it, so it goes here. Beta goes there, so this is alpha, this is beta. And every point, so that's the gate, that is alpha, that is beta. There may be several, of course. We take one point here, P, one point here, Q, and we kind of form the product of the loops, alpha and beta, at these 2 points. So how we do it? We first we start in alpha, go around alpha, the whole loop alpha, until we're coming back to the same point. Then we move to Q along the gate, and then we go along beta, and until go along beta until coming back to Q, and then go back to P. So that's kind of a product of those two loops, and the product is we take such products over all pairs PQ of points P on alpha and Q on beta lying on the same gate. And also there are signs, of course. So there are two kinds of terms associated with the gates and terms associated with intersections inside. And this gives again a well-defined bracket. In the same model as before. And again, if you are sufficiently clever, you make it so that it does not depend on the orientation of the gates. I use orientation to define this product, but at the end of the day, if you skew symmetrize it, so this was dependent on the bracket, depended on the gate orientation omega. Now, if you skew symmetrize it, you get something which is independent of omega. So this is well defined and doesn't depend on omega. And again, it's generalizes the standard Goldman's bracket. When there are no gates, no bad part, you get twice the usual double Goldman bracket. Now the question is what replaces the Jacobi identity? The Jacobi identity is replaced by something like this. You take alpha, beta, gamma plus beta, gamma, alpha plus gamma, beta, alpha. But that's not zero anymore. It is some kind of trilinear form, alpha, beta, gamma, minus the same trilinear form, but evaluated on the triple gamma, beta, alpha. So in this quasi-Lie bialgebras, you have two brackets. One is the usual bilinear, another one is trilinear. Now, in this case, trilinear form comes from the gates. No gates, zero on the right. But when there are gates, there is some interesting trilinear form which has nice properties and so on and so forth. And the same for the co-bracket and the same for the pair, bracket, co-bracket. So there are new algebraic notions, Lie quasi-algebra, Lie quasi-coalgebra, and so on. Now that's all described in detail in my preprints. So actually these are published papers by now. But I think that's an essential part of my lecture. And that's enough for today. Thank you.
Okay, so thank you, Professor Turaev, for this wonderful lecture. So let's start the lecture. So I have a question before I leave it to others. So you talked about this quasi-surfaces, which are essentially surface with some dark unknown part. Now, what about if you take a surface with handles attached to it? Is there any such notion of Lie bracket and this sort of algebraic structure on the loops?
You can view surfaces as quasi-surfaces also. Now, in many ways. For example, you take a surface with boundary, and you draw one or several embedded arcs in this surface, disjoint with endpoints on the boundary. So then you can cut your surface along these arcs. So basically cut your surface along some arcs inside. Then you may say one part
Okay.
is good, and one part, that's the surface, and the other part is black matter. So you declare your surface to be a quasi-surface with those arcs being the gates.
I see.
And
And
that's
now-
an excellent example of a quasi-surface, because it means that if inside your surface you have a smaller surface, you can consider all those brackets associated with this big surface, which is viewed as quasi-surface, using this smaller part, which is still considered to be the surface part. And then you get some new structures in the usual homology of the surface and the usual module of free homotopy classes in the surface. So the surface is, the big surface is the same space, but brackets and Goldman bracket and co-brackets are all different now because they depend on the choice of those arcs.
Okay.
So what is good, what is bad?
All right. Yeah. So I have one more question. So this Goldman bracket has a, is associated to a symplectic structure.
Yes.
Yeah. So what about your quasi brackets?
Well, yes, it is. It's not a symplectic structure, but at least you may ask, what is that notion of a Poisson bracket?
Yeah.
And there is something, there are some tensors, let's say, which do not satisfy the usual Poisson, well, Jacobi equation, but still have some interesting properties. And that's described also in my preference. I wrote some preference paper on this. Probably I didn't call them quasi-Poisson, but it would be appropriate to call those tensors kind of quasi-Poisson structures on the representation spaces.
Okay. Okay, so thank you. So is there any more questions? Okay, I think there is there is no more questions. Yeah, then
Okay.
let's thank, please. Okay, so if there is no more questions, let's thank Professor Turaev again. And
Thank you.
that's the end of the day. So, Nikolai, you would like to say something?
No, thank you for coming, for joining this online meeting, and see you tomorrow.